acceleration for a rotating coordinate system. Okay, so you basically have a rotating coordinate system, and you know if there is a linear system and a rotating coordinate system, the acceleration is not going to be the same. Okay, so in terms of a fixed coordinate system, so if you are rotating, if there is a rotation involved, you know that there is angular acceleration, angular velocity, and then that keeps on changing at every point. And these kind of connections are important to understand, let's say, the motion of the planet or the satellite. Okay, so there is something which also called as the Coriolis force and so on. So this is something which we are going to get a good clarification on this particular topic. So before we start with the derivation part, okay, we're just going to look into the rotating coordinate system part first. So let's consider x, y, z to be the reference frame which is fixed in space. So this coordinate system x, y, z does not move at all. Okay, you have a body axis, you have got a space set of axis, and you have got a body set of axis. So what do I mean by space set of axis? Space set of axis means, let's say, the corner of your room, the wall. Okay, you have got the x-axis, the y-axis, and the z-axis that is fixed, and then you are moving something with reference to that fixed axis. Okay, so if you are moving a ball, let's say, with reference to that fixed axis, and it's rotating, then the axis system fixed with that ball is called the body system, okay, or the body set of axes. So we will represent them as the prime system. So one is the unprimed system and the other one is the unprimed prime system. Okay, so what we have is a reference frame, and that is actually fixed in the body. Okay, so that's the reference frame. So if you consider at, let's say, time t is equal to 0, that means neither the reference frame is already fixed for the fixed space system, but the body system is not moving at time t is equal to 0. Okay, so their origins will coincide and the base vectors will also coincide. Please remember that whenever we are defining the position of that particular point, we are going to use the concept of position vector. And then what happens? The body slowly starts rotating. And when the body slowly starts rotating, you know that the prime system will change its position with reference to the fixed coordinate system. So this is what is there in this particular figure. So, you know, this is your prime system, okay? And then this is z dash, this is x dash, and then this is z, okay, this is y, and that is x. So whenever we are representing in the direction, we are usually considering y for z cap, I cap would be for x axis, and k cap for the z axis. So this is something which you already know, and we are just going to introduce the dash system now. When I write down I cap dash, it means I'm talking about the rotating frame, and j dash, which is nothing but again the rotating frame, k dash is also the rotating frame. By rotating frame, we mean here that the coordinate system is fixed with the body. Okay? So in simple words, when the body usually rotates, we have got the prime system, which will rotate with respect to the unprimed system. Okay? So you can take two pen together and then hold them straight, and then you can rotate one of the pen, keeping other pen fixed. So that means the pen which is rotating is in the primed system, okay, in this particular example, and the pen which is fixed is actually nothing but the space set of coordinates which is fixed. So the rotating pen is rotating with respect to the fixed pen. Okay, so that is the idea here, basically. So when you want to define the position of this particular p, it is nothing but p x y z. It is nothing but in the space set of coordinates. Okay, and any point in the unprimed system. So we usually just keep on telling it as the unprimed system. Okay, so any point in the unprimed system is nothing but p. Okay, so it will basically be defined by this space set of axes or stationary coordinate system. It depends on what kind of term are used in different books, but I've tried to include all the terms possible. Okay, and it is given by the position vector r1. So that's something which you already have seen in the first unit in vectors and so on. So this is the basics, okay, of understanding what is the prime system along with the unprimed system. So now what happens is, if we are considering time t is equal to 0, okay, so I'll just give a very small brief here. If time is t is equal to 0, just let's be clear, okay, the position vector is for that particular point p when the body set of coordinates and the space set of coordinates are coinciding. the position is I cap kx, j cap y, k cap z. That's the space set. And once it starts rotating, okay, these values will change, of course. But then when it is time t is equal to 0, both r will be either can be represented in this or it can be represented in the dash system also. That is the body set, because both of them are in the same, all the axes are coinciding. Okay. So if you're basically considering a rotating frame of reference, I think this next figure is going to be very important to understand. Okay, so let me just explain this figure first, and then probably we can just go for the derivation. So look into this figure now. Okay, so if you look into this figure, you have got, let's say this is the axis. Okay, this is the axis, and the body is rotating about this axis. So you are saying that it is rotating here. So it will basically follow this circular path and rotate. Okay, so this is the rotation that we are talking about. Okay, there are different parameters that can be derived from here. Let's say at any particular point, okay, the position vector is nothing but capital R. Okay, and the angle that it makes with the this axis, the fixed axis, is theta. After, let's say, a time, okay, it goes to this new position, okay, this position, and now the distance that it has is nothing but r bar plus dr bar. Okay, and this particular distance that we are talking about here is nothing but dr. Okay, dr. Okay, so when we talk about this, and we are talking about, let's say, this angle, this is d omega. You know, d omega usually is a measurement of solid angle, so this is d omega. Let's just do a bit of trigonometry here. So you know, this side can be taken and this side can be considered. Okay, these two sides, sorry, these two sides can be considered. Okay, and if you consider these two sides, what we have here is nothing but the value of sin theta. So this particular side would be nothing but r sin theta. So you can consider this angle theta, and then you consider this particular triangle. So you take this, this, and this. So this length is r sin theta. Okay. So you can use this relation of opposite side divided by hypotenuse, and then find this out result. Okay. So we have these terms now. Let's just do something else here. Now what is dr now? Okay. So before I go to dr, I can actually find out what is sine of d omega. So what is d omega? This is d omega, and I can find out the sine of this. Okay. So you know that this side would be the perpendicular side. This is a very small distance. Okay. This is just exaggerated in the picture, but then this is a very small distance, and this can be considered as the opposite side of the perpendicular distance. So this is your perpendicular side. Okay, and this will be your hypotenuse. Okay, you know that this and this will almost be very close to each other. So this can be considered to be nothing but r sin theta, which is the hypotenuse. So dr by r sin theta is sine d omega. Okay, and since d omega is very small, so you know sine of d omega can be written as just d omega. So you can just cross multiply d omega into r sin theta is dr. So that means I can simply write it down dr, okay, dr, okay, this small distance as r sine theta d omega. So please don't get confused here. This is basic trigonometry, okay. So r sine theta into d omega. So there is a sine term, so that means I can actually take the cross product. So all these are vectors. So dr bar is equal to d omega bar cross r bar. Right? So I've taken the cross product, and then if I want to find out the velocity, okay, which is more specifically the angular velocity relation that we are going to find out, what is the change of dr with respect to time? So it is dr divided by dt. Dr divided by dt. This side also I have to take ddt of that, so it will be d omega by dt cross r. Okay. So this r is there, and then we have got d omega by dt, and then what is this d omega? This is the solid angle we are talking about, this entire. So rate of change of this angle is nothing but the angular velocity omega bar. So this is omega bar cross r bar. So I think this simple one slide will explain a lot of things, a lot of basics which you need. Okay. So this is there. So we know that dr by dt is nothing but omega bar cross r bar. What is this relation? This is the relation between the linear velocity and the angular velocity. So if you remember from your class 11, if I'm not wrong, rotational dynamics, okay, you have V is equal to omega cross R. And of course, wherever the syllabus is being taught with some sort of seriousness, definitely this relation is also derived. So this should not be new for you, but then I do understand that some of us either forgot or this has never been done in school. So I've just revised this, okay? That's why we say that the linear velocity is angular velocity cross product of the distance, okay? So V omega cross. This is the same relation. And now if I actually want to define the direction, because you know at every point or every time t, the direction keeps on changing. So we can simply write it down as d I cap dash by dt is equal to omega bar cross I cap dash. This prime system that we are talking about is nothing but it keeps on changing its direction. Okay, so this is just a notation. So don't worry about it. We are just going to look into the main part now. Now, what we are going to do is we are going to find out the relation for acceleration, which is very important. Okay, so there are some long lines and long derivation that needs to be done. So I'll probably just take one set of equations at a time and try to explain. So let's find out what is dr dt now. Okay, so now it's clear to all of us that yv is equal to omega cross r. We are going to use it. Okay, so dr by dt can be written as d dt, and now r is the position vector, and then we are considering here the body set of coordinates. Okay, so if we consider the body set of coordinate and the space set of coordinate, we are going to find out a relation between them. So what is the aim? The aim is to find out the relation between the space set of coordinates and the body set of coordinates. Okay, so if we write down dr by dt, we can write it down as d dt of the space set of coordinates if we consider at time t is equal to 0. Okay, so I cap dash x dash, j cap dash y dash, k cap dash z dash. Okay, so I think I missed out on too many dashes here. There is a dash here, there is a dash here. Okay, so this is there, and then what you can do is d dt of x dash will be nothing but x dot dash I cap dash is there, y dash and then j cap dash and then this. Okay, so you know that this I cap dash, j cap dash and k cap dash are also changing its direction with time. So that means we just can't differentiate with respect to x dash. We also have to differentiate with respect to I cap dash. We also have to differentiate I cap dash with respect to time, right? J cap dash and k cap dash. So if we do that, we do that by the product rule, okay, of differentiation. So first we take this I cap dash is common, then we take this out and then differentiate I cap dash with respect to t, j cap dash with respect to t, and k cap dash with respect to t. After doing that, we get this, this, and this. This is already there. And then here we can do a bit of modification. Now we saw when we derived v is equal to omega cross r, right? That this can also be written as omega cross I cap. Okay, so this can also be written as I cap dash. So that's actually defining the direction, the velocity in different directions. Okay, so x dash is there, and then it can be written as omega bar cross I cap dash plus y bar into omega bar cross j cap dash, and then z bars into omega bar cross k cap dash. So different components. Okay, I, j, and k are written. So what is this? This is again very simple. You see this. This is x dash omega bar cross I cap dash, y dash omega bar cross j cap dash, plus z dash omega bar cross k cap dash. So you know this is I dash x dash, y dash j dash, z dash k dash. Okay, and then you can just simply write it down to be omega cross r. Okay, where r is equal to nothing but I dash x dash plus j dash y dash plus k dash z dash. So you can just simply write down this relation, and once you have this relation, you see that you actually find out a connection between the linear set of coordinates with the rotational set of coordinates. So in the rotational set of coordinates, we definitely have got omega cross r, and it should come logically, right? This side you have got velocity, the other side you will have angular velocity and the position vector. So you have got the angular velocity and the position vector. But then there are some additional terms which comes into the picture when the body is rotating, okay, with respect to time. So that's important. So what we will do now is we are going to find out the acceleration, okay. But before finding out acceleration, what we are going to do is this. We see that this is basically nothing but a connection between the unprimed and the primed system, okay, unprimed and the primed system. So what we do is we write it down in simple terms. Dr by dt in the unprimed system, okay, is equal to dr by dt in the primed system, right? So you know this is x dot, this is y dot dash, this is z dot dash. So it is all ddt. So it is all ddt, right? And this is nothing but x dash I dash y dash j dash z dash k dash, which is again nothing but r. Okay. So we have to basically remember what is r. So what is r? R is nothing but uh, x dash, okay, and I dash, okay, and then plus y dash and j dash. So we are just going to use this again and again. So I'm just writing this down. I think this is okay. And then plus z dash into k dash. So that's important, right? So if we use these, okay, these expression, we can actually simply write it down as dr by dt plus omega bar cross r. So this is in the prime set because we are using a dash dash there. So we are just writing it down in the prime set of coordinates. And if you're writing down it from the unprime system, we can simply write it down to be nothing but. So I'll just use this as r prime, okay? And this will be a better way to remember this prime, okay? And this will be nothing but the unprime system. So you have a relation between the unprime set of coordinates and the primed set of coordinates, okay? And if you remember your quantum mechanics, okay, or in general idea, we call something as operators. So whenever you say, let's say I want to find out ddt of x to the power n, so ddt is usually called an operator. Okay, so here also we have got an operator. So what is our operator? The operator is this ddt, okay, on the left hand side, and on the right hand side it is again ddt plus omega cross. This is nothing but the operator. So this is the operator that we are actually going to use, okay, to transfer from one set of coordinates to another set of coordinates. So please understand the idea of operators here that we are going to use, okay. So let me just go to the next part where we are going to discuss about acceleration, okay. So as I said, what is the operator now? The operator is d dt is equal to d dash dt plus omega bar. Okay, I've just put a dash here so that I don't need to write down unprimed here. Okay, else I can write down this, oh sorry, primed here. So I can just write down prime and then I don't need to write down a dash there. Okay, so d dash dt is interpreted to mean the time derivative of r, okay, in the rotating coordinate system. Okay, so this is the time derivative of r in the rotating coordinate system. So whenever we are considering a prime system, we are considering the body set of axis, and that is rotating with respect to the unprimed system. Okay, that's very important. Now let's find out what is the acceleration. So you know, if I can just go back, okay, I just scroll up again. You have this relation, and you want to find out what is the acceleration. So what you can do, you can take the ddt of this side, okay, but you know, from the operator point of view, if you take ddt for the unprimed system, that will give you an acceleration. You have to take d dash dt plus omega t from the prime system. You have to take this for the prime system. If you are going to find out the acceleration, let me just repeat this. If you want to find out the acceleration, you have to take the ddt of this dr dt that we already know, that is the unprimed system. So we can take this, but then there is a relation between the ddt operator on the unprimed system and the prime system, and that relation is this, right? So if this side you are differentiating it with respect to time, this side you should differentiate it with respect to time plus an additional term of omega bar cross, and then only you can say that you are consistent with your derivation. Okay, this side is acceleration in the unprimed system, and on the left side it's the acceleration of the prime system. So that's just do it, okay, and that's what the meaning of operator is all about. Okay, so let's go back to the derivation now, and here we are going to look into the different terms that we have. Okay, so this side ddt of dr by dt, that's standard acceleration, right? D square r bar dt square, standard acceleration, right? But then this side I have to differentiate it and use this term d dash dt plus omega bar cross into, of course, whatever is the velocity term. So this is the catch here. Okay, if you understand this, I think the rest of the thing is very preliminary. Okay, it's more trivial, simple. So let's just do the differentiation. So this side, let me just keep it as it is. Okay, this side I don't need to think about much, but then this side I need to just worry about a bit. Okay, but there are certain steps that I should not miss. Okay, so what I do on this side is first, okay, second. Okay. We'll just take this and this, so it will be d dash square r bar dt square, okay, plus, and then what we can do is we can take this with this, okay, now with this. Now you know that this is d dash dt with respect to omega and d dash dt with respect to r. So that means we have to do again the product rule, okay, product rule. So we'll take d dash dt omega cross r, this r is not differentiated with respect to time, plus omega bar cross d dash r dt. The question or the point that you should remember is, I think you already know it, that these are vectors, so I cannot change the order. If omega is on this side of r, it will remain on this side of r. I cannot take it on the other side, right? The order cannot change, right? So this is done. So I have differentiated this with this, and I have also considered this and this. So both are done now. Okay, now let's do this part. Omega cross d dash r bar dt. So omega cross d dash r bar dt plus omega cross r. I think this term you might have seen it before also, but we are going to discuss this later. Omega bar cross r. Okay. So what is this term? Acceleration in the prime set. So it is a dash, can be written. Even if you don't write, just put it this way, fine. Look into this now. Omega, and this is also the same term. So this is the second term. So these both are same. So I can just add them up and I can write down 2 times omega of d dash r dt. Okay. Next, you have got this term. So I've just written this term, and you are just left out with this term. So this term is also written here. So it's perfectly fine now. Okay, I think this is a very simple idea. Yeah. Okay, we're just using the product rule of differentiation. Okay, so that we can actually differentiate it out and then find out the different terms. If you look into it carefully, all these 4 terms will have the dimension of acceleration. That means all these 4, 1, 2, 3, 4 will have dimensions of acceleration. That means they are representing acceleration, and that should be right, because left hand side is acceleration, so the right hand side should also be acceleration. But all of them has got a specific meaning. Okay, so you know, whenever a body is rotating, it is not a simple case of a normal acceleration. It is angular acceleration. But then, if depending on what kind of condition you are considering, okay, you will have different components of that acceleration that will add up to all the accelerations possible. Okay, so this is where your higher order understanding of physics comes into the picture. So we have got 4 terms, and then we can actually have a look into what these 4 terms actually represent. Okay, so I'm just going to discuss some of them right now. Okay, and it should not be very complicated. So we have this, we are just considering this equation as the baseline and trying to understand what are the 4 acceleration terms representing. Okay, so if I can just keep this part here, if we just take this d square r divided by dt square, which is represented by a dash, this particular term. Okay, this is nothing but acceleration in the prime system. This is there, done. Then I have taken another term which you might have come across again and again. This is the centripetal acceleration. So these are the different parts of the acceleration that it has. Okay, and these are all conditional, depending on whether the velocity is constant or not, whether the velocity is varying. Okay, so depending on these factors, you will have a centripetal acceleration. You might not have a centripetal acceleration. But then, if you want to derive it, you have to derive the general case and then put into specific pictures, okay, specific examples, and then try to know whether the centripetal acceleration will be valid for that case or not. Okay, so we'll just look into that in very short. Okay, so this is the centripetal acceleration, again very important. Okay, what are the 2 other terms left? One is 2 omega cross d dash r by dt and d dash omega dt cross r. Okay, we're just going to look into these 2 terms now. Okay, this is very important. So one of them is actually called the Coriolis acceleration. But then before we shift to this, let me just simplify this omega cross r. Okay, so if you just try to simplify it, okay, let me just go at the bottom first and then I'll come at the top. So omega cross r. Okay, and these are the steps which I have not found in most of the books, but I tried to write it down so that it's more clear to you all. Omega cross r, you know, there is it's basically a triple product. Okay, so omega cross r is perpendicular to the plane containing omega bar, right? So if you have got A cross B, it will be perpendicular to the plane containing A or the plane containing B. So omega bar cross omega cross R is equal to omega cross R. So this is actually omega and omega cross R are perpendicular to each other. So they are making an angle of 90 degree. Okay. So they are making an angle of 90 degree. So it is sine of 90 degree. Okay. So you know sine of 90 is 1. So you can just simply write it down as omega bar cross R. Okay. So you can simply write it down as omega, and then omega cross r can be written as omega r sine theta. So it is omega square r sine theta. So you've got rid of the cross products now. We have just written it in terms of the angle. Okay. So omega square r sine theta. Okay. So you can just go back. Okay. Go back on top, because if I don't explain this, then you will ask me why I got this as omega square r. That's why I've just written it down. Okay, in separately. So we have got the term omega cross r sine theta. Okay, and then what we can do is we can use the traditional relation v bar is equal to omega cross r. Okay, and then v bar can be written as omega r sine theta. And if we just square both sides, we can simply write it down as omega square is v square by r square sine square theta. So this omega square can be replaced as v square by r square sine square theta into r sine theta is already there. So you can just cancel out this r and r square, and sine theta and sine square theta. The simple term that you get is this. Okay. So number of times when we actually talk about the acceleration, okay, or the centripetal acceleration, okay, this is also the term that is v square divided by r. If you remember, mv square by r will actually represent the centripetal acceleration. Okay, but then again it depends on what kind of angle it has. If the angle is 90, okay, if it is 90, then of course sine theta is 1, so it's just v square by r. So that's centripetal acceleration mv square by r. Relation you already know it, but then we are just deriving it here. Okay, so that's very important. So you know this central force or the classical mechanics doesn't divert much from the basics that you already know. Okay, if you just recall certain things, and then these things should not be very difficult for any of you. Okay, let's just go to the second term now. The second term is actually 2 omega bar cross d dash r bar dt. Okay, so the second term is this. Okay, so this is again important. Okay, and what does this represent? Is this present? What happens is this present only when the point r is moving in the prime system and is called the Coriolis acceleration. This is actually called the Coriolis acceleration. So what happens is that the prime system will be moving with respect to the unprimed system. Okay, but then if the point itself is also moving in the prime system, there is another acceleration which comes into the picture, which is called the Coriolis acceleration. Okay, so I may take some examples in the next class, okay? But then today's class, let me just finish off with the definition of all the terms that we have. Finally, we are left out with just one term, which is d omega bar dt cross r bar. And this is nothing but the acceleration produced by the angular acceleration of the prime system with respect to the unprimed system. So this is another term. Okay, so you basically have a two coordinate system. One is this, okay, and other one has rotated. Okay, the other one has rotated. If you take a different color, the other one has rotated. So it has rotated along this, sorry, and along this. So you know this has rotated. So that means this prime system is also moving with respect to the unprimed system. And if it is accelerating, remember, if the acceleration is not there, that means if the velocity is constant, then of course that term is not there. But then if the velocity is not constant and it is accelerating, then this term comes into the picture. This is the reason that we have the fourth term. Okay, so this is exactly where we stop. But then this is important to understand that there are four terms of acceleration. So from maths point of view, okay, or from a derivation point of view, maybe it's okay if you just stop there, okay, with the derivation of acceleration. Stop it here, that's fine. But then, you know, if you're writing down a physics answer, you have to explain what are the meaning of these four terms, okay? You are bound, okay? You are morally bound to write down the answer. Even if you are given less marks, still you should at least explain what are the four terms, in short. So you can just simply say that this is nothing but the acceleration in the prime system, the first term, okay? The second term is nothing but the Coriolis acceleration, okay? The third term is nothing but the centripetal acceleration, and the fourth term is actually nothing but the acceleration of the prime frame with respect to the unprime frame.